meeting. We'll be having this meeting today, tomorrow, and the day after. So thanks to many of you for joining from all over the world. Just to give you a very quick overview, this meeting provides an open forum for the attendees, users, system administrators, researchers, and engineers, and students to discuss and share the knowledges on using MVAPICH2 libraries, including the different versions like MVAPICH2X, MVAPICH2 GDR, Azure, and the AWS, and also OSU, INAM, and OMB, and experience with large-scale systems, usage with a diverse set of applications, both scientific and AI, exposure to tuning and optimization, and sharing common knowledge and troubleshooting procedures. So we have a very exciting program with all of people lined up. In the 3 days program, we have 35 speakers from 18 organizations. As you can see in the list, all the names of the different organizations. And attendees wise, as of today morning, we have 326 registered attendees, around 175 organizations. Some of the emails clearly don't reflect the exact organizations, but we have attendees from 21 countries, from 5 continents. And in case we have missed your country, it's not listed, please send us a note and we'll be happy to add it. So today's program is mostly focusing on tutorials. We'll be starting with the tutorial from ARM, followed by NVIDIA Mellanox, and then from the OSU, focusing on the OSU INAM, which is the InfiniBand network and monitoring tool. Then we'll have a half-an-hour break. These all the times are US EDT, so please adjust to your local time. And then we'll have a tutorial from Microsoft Azure, and followed by a tutorial from Broadcom. And finally, another tutorial will be there from Ohio State, focusing on the MVAPICH2 library. So a couple of guidelines, as you must have received the emails. Thanks for joining over the Zoom. Today morning, I think there has been some outage in the Zoom, especially in the US East Coast, and might be some other place in US. So if you encounter any difficulties, please let us know. I think you can still join it through the app. I think the website is having some issues. Hopefully this will be resolved very soon. As we indicated, the charts are disabled. We have dedicated Slack channels have been created to facilitate discussion with speakers and the topic. And you must have received this link through the registration. This is the Mark 20 Slack link. Please feel free to log in and ask question answers there, or use the QA boxes in the Zoom webinar. So I'd like to thank all our sponsors here. Without their help, we could not have put together this program, especially all these sponsors: ARM, Broadcom, Microsoft, NVIDIA, Scalable Solutions, ParaTools, Ohio Supercomputer Center, and the Ohio State University. So with this, let me introduce our first speaker of today, and just 1 minute. So today we have John Linford, who is the director for HPC applications at ARM. So he will be talking about performance engineering with MVAPICH2 and ARM's scalable vector extension. John is ARM's director of HPC application. He leads ARM's global HPC field engineering team and explores and predicts the performance of future architectures relevant to HPC. His research interests include emerging computer architectures, compilers, code generation, performance analysis, and numerical simulation. He has developed tools for chemical kinetic simulation, rotorcraft engineering, software performance analysis, and software environment management. So let's give a very hearty welcome to John. John, would you like to share your screen and then get started?
Thanks very much. Let's see, I'll go ahead and share the whole screen here. Is this coming through all right?
Yes, perfect.
Excellent. Start the presentation. There it is. Wonderful. All right. Thank you very much for the kind introduction. Thanks, DK. Thanks, Harry, for putting this event together. This is always a great meeting. So I've been looking forward to it for some time. I will be speaking about a couple of topics, mainly.
Sorry, I'm not able to at least hear you, John.
Oh, I'm sorry.
No, like you're fine. Like we are able to hear you just fine.
Yeah. Okay.
Okay.
Go ahead.
Should I continue?
Yes, please.
Yes.
Okay, great. So I'll be covering two topics. First, performance engineering within MVAPICH2 on ARM platforms. And secondly, ARM's scalable vector extension, which is the high performance vector instructions that enable things like the Fugaku supercomputer. My objective here is to provide enough of a starting point that attendees to this talk can go on their own time and pick up more hands-on materials and deep dive into some of these topics, since our time here is limited. So I've brought more slides and more materials than I'll be presenting today, but all of these materials are available to you, and the training cluster will be available all week long. So I hope everyone will take advantage of that. To start, all of these slides, as well as the hands-on materials and code samples, are available at this URL, which is also pasted into the Slack channel. And the schedule for today is roughly evenly split between ARM's Alenia Studio, which is our toolkit for performance engineering, and an introduction to SVE, the Scalable Vector Extension. I'll do my level best to keep on schedule here. Like I said, I've brought a lot of slides. So if you'd like to get started with this while I'm talking, here how you access the cluster. Essentially, SSH with the username student and the password training, as described here. When you log in, you'll automatically be assigned a student ID, which will give you your own unique username and password. So although you're logging into the head node with the same username, everyone will have their own space and their own isolated compute node to work with. So each of you will get a private AWS Graviton2 instance, which is a pretty decent little server. So you should be able to do all the hands-on there in isolation. Once you're logged onto the cluster, you can load a couple of modules. We have MVAPICH2 version 2.3.4 configured with either the GCC 9.3 or with ARM's own LLVM-based compiler, the ARM Linux compiler 20.2. Load either one of these modules, also load the Forge module and the ARM instruction emulator module, and you'll be all set to do the hands-on materials that are available in the cluster. I can hear some typing in the Slack channel. To stay on schedule, I'm going to pause about halfway through the talk and take a quick look at the questions.
John, like what we can do is if there are any questions, we can like read them out to you so that you don't have to switch between the presentation and the Slack channel.
Oh, perfect. Yeah, thank you very much.
Yeah, thanks.
So in addition to accessing the training cluster, I also suggest that you install the ARM Forge remote client on your local machine. This will enable you to connect a graphical user interface to the remote training cluster and do the debugging and the profiling exercises. You don't need it for the SVE exercises or the exercises involving only the math libraries or the compiler. But if you want to use Forge, this is a really good way to do it. And I'll actually walk through that in a minute. Okay, so hopefully that's enough to get started with the hands-on. Now I'm going to switch gears a little bit and provide a little bit of background of ARM and HPC, because we're relatively a newcomer to this space. But ARM has already gained a lot of momentum in HPC. So starting in about 2018, ARM announced the Neoverse line of CPUs, which is a server class of intellectual property meant for ARM partners to build high-performance systems, server system, hyperscaler systems, anything really that's bigger than a phone or a client device. And since that announcement, we've had a number of key wins that are highly relevant to HPC. For example, NVIDIA has fully ported the CUDA stack to ARM platforms. So ARM is an officially supported platform for NVIDIA GPUs. They work out of the box with no special caveats or special considerations. They're on equal footing with any other architecture out there. AWS announced the Graviton and the Graviton2 processors. The Graviton2 is a very decent platform for commodity HPC. It does a pretty good job. Ampere has announced an 80-core server SoC with 128 cores coming later. Again, a very nice chip. I've had the opportunity to play with this a little bit, and it's a pretty compelling HPC platform as well. And of course, Fujitsu used ARM intellectual property to build the Fugaku system, which is #1 on the top 500 currently, and scored very well on most of the benchmarks that supercomputers are measured by. It was a very compelling proof point for the maturity of the ARM software ecosystem. If we look at a typical ARM software stack, you see that everything is available on ARM. It's no different from x86 or Power. We have the full end-to-end HPC software stacks available. And this has led to the growth of a very rich and complete application ecosystem for HPC, where if you think of HPC as a platform for delivering solutions for different areas like chemistry or weather or even AI and ML, ARM is really gaining a lot of ground in this space. And we're starting to build we're starting to see more and more pull from commercial partners, automakers, aerospace engineers, are coming and asking, where's my ARM server? Because they're seeing the benefit of running on that platform. It's been very interesting. Fugaku, which I mentioned, of course, fastest supercomputer in the world by some measure back in June. Very interesting proof point. I'm going to take a moment to talk about this chip because it really demonstrates, the differences, I think, between ARM and HPC and other companies out there. ARM is not fully integrated. Fujitsu, when they built the system, it really is a Fujitsu design. It uses the Fujitsu microarchitecture, and they worked closely with ARM to develop SVE and define the instructions that were necessary for the Japanese workloads. The chip that they've come up with, the A64FX, has a lot of really unique properties. For one thing, there's no DDR on it. It's only HBM. And it's more like 4 chips in a socket, to be perfectly honest. Each of the A64FX chips is split into a core memory group, a CMG. Each CMG has a stack of HBM, and it has 12 plus 1 cores to manage it. And you program it as if each CMG was essentially a socket of its own on the board. Now, because of this really unique architecture, you might find that you might think that it was challenging to spin up an ecosystem for something so bizarre in a sense. But this is the advantage of using ARM intellectual property and using the ARM instruction set. Fujitsu had complete freedom to build a unique architecture squarely aimed at HPC, and the software ecosystem was already mature and active when they turned on the chip because it used the ARM instruction set. So this chip can boot any standard Linux. It can run Windows. It can run any of the basic HPC applications that have already been ported to ARM. There's not a lot of work involved in getting things to run on this chip at all because they use the ARM instruction set on the front end. So I think this really demonstrates the value that ARM brings to HPC. Another interesting proof point was the Vanguard system by HPE at Sandia Labs. This was the first supercomputer, first ARM supercomputer to post on the top 500. And it's more interesting, I think, to this audience because it does use Mellanox InfiniBand. It's EDR, ConnectX-5. So they have MVAPICH2 on the system. And indeed, every ARM system that has InfiniBand does use MVAPICH2, as far as I know. It's well supported on the platform. AWS Graviton2, you can also run MVAPICH2 here. And I understand there are MVAPICH variants that specifically target the EFA, the Elastic Fabric Adapter for AWS. I expect we'll be seeing some advances for AWS in that space very soon. Graviton2 is a very solid platform for doing commodity HPC. In terms of raw performance, it usually stands alongside the other x86 instances that you get from AWS, so the C5Ns and the C5s. But then the price is much lower. So the in1 cores consume far less power than the x86 cores, and they're cheaper to manufacture. So AWS is able to offer them a much lower price. For commodity HPC workloads, this is key because the folks who are developing their Formula One car or their new aircraft, they don't much care if the simulation finishes in 4 hours or 6 hours, as much as does it finish in $50 or $70. So ARM has become a very compelling platform in this space as well. So ARM is gaining momentum in HPC, especially in the commodity HPC space. What does it look like to bring applications to this platform, and especially if you start to add things like InfiniBand to the mix? I want to pause quickly before I get into performance engineering and just show you something in my terminal, if I can bring it up. Now, unfortunately, I'm not able to offer A64FX access for this tutorial. I had hoped that we could do it, but at the moment there's no A64FX or no publicly accessible A64FX cluster in the United States, and the publicly accessible clusters in Japan are under a Japanese export control that make it very difficult for US, well, not necessarily US, but it makes it difficult for public access overseas. So the A64FX system I have here, it does in fact support InfiniBand. And this is the point I wanted to make, that these ARM systems, even though they seem strange and odd, the way that we go about performance engineering for them and we may be tuning for them is completely familiar. It's exactly the same as before. In fact, the only way I could tell that I'm on an A64FX at all is if I took a look at the proc CPU info, and I noticed that it has here 48 cores. The CPU implementer is the ASCII code for A for ARM, and it implements SVE. This is pretty much all the hint you'll get that you're on an A64FX. If I take a NUMA control-H, I can see that there are 4 different NUMA nodes, one for each of the CNGs. This is, like I was saying, that on an A64FX, you really think about each CNG more as a single socket in the traditional sense. There are some hardware advantages to not actually being single socket. There are hardware synchronizations that can be done between CMGs much faster than between multiple sockets, but that's the programming approach you would take. So I just wanted to demonstrate that as a way to show you that even though we're not using A64FX for this hands-on, we'll be using the Graviton2. The stuff that we're implementing on Graviton2 translates forward to A64FX. And if anyone on the call has access to this platform, you should be able to do the same hands-on exercises on an A64FX. You'll also be able to do them when some of the publicly accessible clusters come online in the very near future. Okay, back to the slides. So, performance engineering. Performance engineering on ARM is much the same as it is on any other platform. To identify and resolve performance issues, you begin by profiling your code. Profiling and understanding the performance of the application is critical. And it's astonishing how many times I've sat with applications experts, people who come from, they're experts in their domain. They may be brilliant chemists or physicists, and they've written a code and they'll swear up and down that they know exactly how their code performs. And then you show them a profile of their application running at scale and they're completely amazed that, that was not at all what they expected. Codes, you really have to start with profiling to begin your performance optimization loop. Now, once you've identified an area of possible performance improvement, for example, in file I/O or in communication or in memory or in compute, then you should focus on that one aspect of performance. Only make changes related to the one aspect. So for example, if I have an application and it seems to be spending a great deal of time in file I/O, then I might want to look at how could I use local burst buffers? How can I change the data formats? How can I use maybe an in-memory file system? Some of the standard tricks for improving file I/O. For parallel I/O, you implement MPI I/O, something like this. Once you make those changes, go back and profile again to see the effect of those changes. And then just continue looping in that cycle until you feel that the performance in that aspect has been improved sufficiently, and then move on to the next one. The 50x, 10x, 10x, 5x numbers I've shown here are the slowdowns that I've personally seen in real world applications due to that aspect of performance being done poorly. So I'm not saying that if you improve file IO, you get a 50x speed up. I'm saying that if I wanted to slow your code down by 50x, I would start by goofing up your file IO. I can promise you that you will get a massive slowdown by doing file IO badly. Similar with communication. If you are using lots of blocking communication, all-to-all communication where it's not necessary, an easy 10x slowdown. So start by optimizing there and before you're moving on to something like compute. Now, there's a lot of performance engineering tools in the ARM ecosystem. A great way to find these is to take a look at the VIHPS tools guide, which is published periodically throughout the year and updated constantly. If you open up this, this guide, which I've linked at the top, you'll see in the margins that for every tool listed in the guide, it will show the architectures it supports, it'll show the features that are supported by the tool. They are, you know, these margin annotations are not always complete, but if you see one there that says, you know, ARM is supported or GPUs are supported, then you know for sure that it at least does that and possibly more. I would encourage you to start here if you're looking for a good free open source tool. Lots of very good tools there, including some I think will be presented here at the MVAPICH users group this week. Now, ARM provides a commercial solution for performance engineering on ARM and x86 platforms. This is called the ARM Alenia Studio. If you're working on ARM solely, then the ARM Alenia Studio includes compilers and performance libraries that are meant to be used on ARM, for ARM, and they're not cross-platform. They just work only on the ARM architecture. But the performance engineering tools are cross-platform. They work on x86, Power, NVIDIA GPUs, AMD GPUs. They work across multiple platforms, so you can do an easy apples-to-apples comparison of performance across many different architectures and many different interconnects. This is exactly where I would go if I wanted to see the performance difference of, say, MVAPICH2 on EDR versus maybe OpenMPI on OmniPath or something. I would take a profile on the different architectures using the same ARM Forge tool, and then I can compare those directly and know that I'm getting a fair comparison without any tool bias for the platform. Now, these tools they're not free. You do have to buy a license, but I don't want you to get the sense that you can only use licensed tools on ARM. Like I said, if you want free tools, please go here. If you want commercially supported tools, this is a good option. So Forge was not always at ARM. Many of you might know Forge from its original home at Alenia, which was Alenia software was purchased by ARM a couple of years ago. And Alenia was very successful. They basically made their tool a de facto standard for HPC development. DDT and MAP were omnipresent and found on the majority of the top 500 machines in the world. This is one of the reasons why they continue to be cross-platform, because ARM is committed to maintaining support in DDT and MAP for those other architectures. And DDT and MAP, you know, they really do provide very state-of-the-art capabilities for debugging and profiling with an aim of being fully user-friendly and fully scalable. There's a lot of good profilers out there, but many of them don't scale beyond a few hundred nodes or maybe a few thousand nodes. MAP is designed from the beginning to show you compute time, show you time spent in communication, time spent in I/O, and do it at many hundreds of thousands of processes with a mixture of OpenMP and MPI and pthreads and CUDA and all kinds of parallelism coming together. That is a design goal for this tool. DDT has a lot of cool features. And again, I'm mostly throwing this out here in the hopes that the people on the talk will pick up the hands-on materials that I provided on the cluster and in the Slack channel and go work through the hands-on so that you'll be able to experience some of these features for yourself. So I'm not going to spend too much time here except to say that it's a very featureful tool. the best way to use it is to connect with your remote client from the local system to a remote cluster like the training cluster we provided. Some of the highlights is that it does support GPUs. It's very scalable. Also supports memory debugging. So you can do memory error detection, out of bounds detection with guard pages, memory leak detection, and you can do this at reasonably large scales. Also supports single or multiple core files and different types of scalable launch, either PMIX or MPIR. Now, because you have all this together, it makes it very easy to answer some simple questions. For instance, which MPI rank has misbehaved and caused the program to crash? Or what are the source code locations that are related to the cause of this problem? You can trace back through several layers of the application across multiple languages, C, C++, Fortran, Python, and find out what happened in your code that caused it to crash. Now, if you do memory debugging, here's a quick side note specific to MVAPICH2. You need to set this environment variable to be the maximum job size you'd expect if you're going to do memory debugging. Don't set it as a system-wide default, just set it as needed per job. And do preload the memory debugging library when you launch. Now, this is one of the Forge specific things just for MVAPICH2. You can also run DDT in an offline mode. There's a hands-on exercise that'll show you exactly how to do that. This is a nice way to uncover the cause of a crash that only manifests after a long run, or maybe you could incorporate this into a CI/CD system which runs every night, so that if an error does occur, you don't have to run the job again to discover why the error occurred. You'll have a report at the time that the job failed. Now, I've mentioned the remote connect a couple of times. The reason for this is, these are graphical tools, and if you use a graphical tool over X11 forwarding or VNC, typically the user experience is very bad. The latencies can be bad, resolution can be bad. It's just not a very comfortable way to work. So Forge is designed to provide a local client that uses the local CPU, the local GPU to render everything, and then communicate with your job over an SSH tunnel. So there's no special daemons running in the background. There's no special services you have to install. You don't need root access. It's all standard SSH stuff. And it connects to the head node of the cluster and communicates with the job running on the compute nodes on the back end. And this is probably my favorite example of just how well this works. So I was able to use the Forge front end while I was flying to the Pawsey Supercomputing Center in Australia. So I was somewhere over the Pacific at 41,000 feet and 555 miles an hour. And as you can see, my network characteristics were absolutely terrible. And even under these terrible network conditions, I was able to use the Forge front end connecting to the Pawsey supercomputers and get reasonably good experience there. So if anyone tells you they can't use Forge because the GUI is a blocker for them, I just say that can't possibly be the case, right? There's no technical issue here. Even in the worst of network conditions, you can run this thing because it takes advantage of the local CPUs and GPUs. You're not really piping any compute over the line, just communication to the job that's running on the remote cluster. Now, to install the remote client, you just go to the link described. If you're on Linux, you install the whole Forge. ARM Forge itself incorporates the GUI, so you just use that. On Windows and Mac OS, there's a stripped down version, which is only the Forge GUI, and you'll find that at the bottom of the page. Now, once you have that going, you launch it by opening a remote connection. And rather than show slides, I'll actually walk through this very quickly. So let's see here. I'm going to click on the right thing. So I have my Forge remote client. And I would go to remote launch, configure, and add a new configuration. Now this to connect to a remote server, I need to know the host name, the username, and the location of the Forge installation on the remote server. Now, fortunately, our training cluster is configured to tell you these things when you first log on. So if I spin over here for a moment, let me go ahead and log into the training cluster. Now, to remind you, this is SSH student at cluster.org with password training. Oops. Yes. So I'm going to go ahead and do that. Logging in. Oh my goodness! Wow. So we've already got several people in the cluster. Now, I can say a few minutes, say a few words here. This cluster is using AWS Graviton2, so we're using an auto-scaling group in AWS to provision new compute nodes as needed. I had pre-allocated 20 nodes, but evidently we have a lot of interest here, so I've already picked up more than 20 nodes. I do apologize. My daughter's interrupting. Let me pause for just a moment. I'm very sorry. I've lost there.
This is a good problem to have. People are actually interested in the tutorial. So thanks, guys. So while John tries to create a new instance, are there any questions? Okay. So I do. Okay.
I'm back. This is the challenges of working from home. My 6-year-old daughter was asking for some help. Let me check what is going on with this. Desired capacity is only at 6, so let me change that. Let's get that up. All right, coming back to this.
So,
sorry,
John, Samir is having an issue logging in. So on the Slack channel, he mentioned that opt ARM Forge 1905 libexec DDT remote D is not available. There is no such file or directory.
Let me go have take a look. Oh, wrong Slack. Launching ARM Forge get. Well, you've provided the wrong path. So opt ARM Forge 1905. Sorry, where did you find 1905? If you take a look at the message when you log in, here, let me show the slides again. So for example, when you first log in, you'll see that there's a box here that says ARM Forge remote launch settings. That will give you the path to the login. This is just an example. This is not the thing you want to do. Actually log into the cluster and actually look at what the message is and use that instead of what you see as an example here.
Thanks, John. Samir, okay. Yeah, I think that worked for him. Thanks. Great. Thank you, John.
Okay, so let's see if I've got a new instance yet. Nope. So the node is still being provisioned. I probably should have stolen one of these ahead of the schedule, but that's okay. I brought slides. So while that's spinning up, so after you connect, you'll get a confirmation that the remote launch test is completed successfully. And from there, you can use Forge locally on your system connected to the remote cluster, just as if it was running on the local box. So DDT is our debugger, map is our profiler. To use map with, typical usage is map-profile, and then you give your MPI run command. With MVAPICH, it's slightly different. You don't provide the MPI run part of the command line. So you would just say map profile in 48 example, and you'll be off to the races there with your profiler. So MAP is different from most profilers in that it's a statistical profiler. So you're only going to get a high-level summary of the performance of your application. It can't break down into individual MPI ranks and OpenMP threads. DDT can, the debugger can drill down into individual processes, but the MAP profiler aggregates all that data together to keep the runtime overhead low and to keep the profile size small. So this is a lossy sampler that's basically building a statistical picture of the performance of your application over time. And that is sufficient to identify the major components of performance in your application. It's a good way to get started with figuring out, is it mainly compute? Is it mainly communication? Is it mainly file I/O? What is the primary reason for the application slowdown? Once you've identified that, it might be clear from just looking at the profile how to move forward and optimize performance. If it's not, then this is a good time to pick up a more detailed profiler, like any one of the ones I've shown in the VIHPS tools guide. There are many tools in there that can drill down into individual processes and really give you, cycle-by-cycle instructions on how your application is performing over time. So MAP is a good starting point, and maybe it's all the tool you need, but often I find that it's a good place for me to get a broad sense of where my code is spending time and then move forward into a more detailed analysis. Supports hardware counters, and it also supports Python. So multi-language profiling, this has been very useful to a couple of our clients. Right, in the interest of time, I'm gonna keep moving forward. There's another tool called Performance Reports, which is a sort of a consultant in a box. It ingests a MAP profile and then spits out a report, which in a very high-level summary, will describe if your code is compute bound, if it is MPI bound, where is your code spending the most of its time. This is a great starting point if you open up the MAP profiler and it just doesn't make a lot of sense. You're not sure exactly what you're seeing. Put the MAP profile through the ARM Performance Reports tool, and it will give you a high-level guidance of where you might start looking to begin that performance optimization cycle. So you see things like CPU time, including SIMD time, so time spent in AVX or AVX 512 or SVE even. You also get you can also see time spent in collectives versus time spent in point-to-points with MPI, and OpenMP time as well. So if you're spending too much time in synchronization or the overhead of the MPI of the OpenMP parallelism itself, that will be called out in the report. So a very, very useful feature for getting started. A couple things you need to know about running Forge with MVAPICH2. Like I've said, you need this NV2 on-demand threshold set to the maximum job size you'd expect if you want to do memory debugging. A couple other considerations here. I'll just leave these for reference. Now, the hands-on exercises, each hands-on exercise comes with a run script, which has already been tailored for MVAPICH2 and tested on this cluster. So if you need further details on how exactly to run Forge with MVAPICH2, you can also look at those run scripts. Hands-on. So let's see now. Have I got a node yet? I have. Okay, so I've been allocated a new node. My student ID is number 1, so I'm student 1. And this is telling me that if I want to connect Forge, I would use these settings. Username student 1. I'll go ahead and put that in here. Remote installation directory opt arm forge 20.1. And my password is going to be training !001. So I'll test the remote launch. Asks me for my password, I'll enter it, and it works. So once I've configured the remote launch settings, I can choose the remote launch configuration from this dropdown. It'll open up a SSH tunnel to the remote cluster. And you'll know it's connected because you'll see the license serial number up here in the corner. Now, anything I do on the remote cluster will actually be rendered on the local Forge interface. So if I pick up one of these examples, let me take up the Forge example, and I'll go run a map profile. And like I said, each one of these examples has a run script, which will just show you how to run. So I'll go ahead and run here. Oh, of course, I've forgotten. If I list my modules, when you first log in, there are no modules. So just as this slide showed, back towards the beginning, I showed that we have some modules to load. I'll load modules for the ARM Linux compiler. And I'll load modules for Forge. Oops. And I'll throw in the ARM instruction emulator as well. All right. So now I have GCC 9.3, ARM Linux compiler, MVAPICH2, everything's ready to go. Now I should be able to run this example. So using map with the -- profile tells map to generate, to profile the application and then save the results to a file offline. So this is going to run here, takes just a couple of seconds. And soon that profile file will be available to open and look at. You can see we've generated a map profile. We've also exported it as a JSON file for good measure. So now I have this map file. If I go back to my GUI and let's see here, go to map. And load a profile. This, you can see that my file system is actually on the remote system. So student 1, Forge, profile, map. So I'm loading the file that I've generated there. And again, this GUI is not over X11, it's not over VNC, it's being rendered locally using the data that's streaming off the remote cluster. So you'll see that there's no lag, there's no loss of it. Actually works very well. So the first thing map's going to do is look for this line of source code where most of the time was spent, and right away it's identified the innermost loop of this matrix multiplication kernel as the place where almost 75% of the runtime is being spent. If I take a look at this top bar, I can see a breakdown between compute, which is green, and communication, which is blue. We can see in a nice little way that this blue up here is our MPI init call, followed by some matrix multiplication, and then the blue at the end, let's see if I can move this out of the way, the blue at the end there is our MPI finalize. Then this tiny little bit of orange there is a little bit of file IO that the code is running right at the end of it. Now this is a very simple example. I don't want to get into too much detail in such a short amount of time. But please do work through the hands-ons, just as I've shown here. Each one of them comes with instructions, so should be fairly straightforward. All right, so I've shown how you can use Forge, what you need to do to run Forge with MVAPICH2. This cluster is going to be available all week, at least, possibly 2 weeks. Depends a little on the training schedule. So do please use it anytime as you can. And if you have any questions, just let me know. I'm available by email. So I'm going to shift gears a little bit now and talk about SVE. The real enabling technology in the Fugaku computer that really allows it to hit the #1 slot on the top 500 for the HPL is the scalable vector extension. This is ARM's way of doing vector instructions, similar to Intel's AVX, AVX2, AVX512. This is ARM's answer to that kind of instruction. So first, the scalable vector extension. What makes it a scalable vector extension? Well, unlike fixed width instruction sets like AVX2 or AVX512, which have a fixed number of bits in the vector register, there is no fixed number of bits in the vector register for SVE. That is left up to the hardware implementer. So whoever is licensing this technology and implementing it into their CPU, they get to decide how wide the vector should be. It can be anything from 128 bits up to 2K bits in increments of 128. So you can have an SVE implementation, which is 384 bits. That's perfectly acceptable. And it uses exactly the same instructions. This is a key point, that if you have different number of bits in the vector register, the assembly language is identical regardless of the number of bits. So I can develop code on a platform that has maybe 128-bit vectors, and then run it on a platform that has 512-bit vectors, and without recompiling, without anything, it's exactly the same binary code. At runtime, the code will readjust for the new vector bit width. Now, using this sort of scalable approach has allowed SVE to address many of the traditional barriers to auto-vectorization. So I'll touch on some of those features, but generally speaking, using this, by taking the idea of how many bits per vector off the table, SVE makes it easier for the compiler and the programmer to write code that vectorizes well. And this is a completely new approach to vectorization. It's not an extension of existing architectures or existing fixed width instruction sets like Neon or AVX. It is a completely different new way of going about things. So like I said, by taking the bits per vector off the table, that makes SVE a vector length agnostic programming model, where you as the programmer will write your code once, and you can write it using intrinsics, you can write it using assembly language, you can use it in a high-level language. It doesn't matter. After compiling that code, it gets compiled into instructions that are vector length agnostic. So these instructions, when they get run, will automatically scale up or down to fit the hardware that is available at the time. And this means you don't have to rewrite hand-coded SVE assembler every time you port to a new platform. You don't need to have a different implementation of your computationally intense kernels for every different type of CPU out there. You just write it once and then you're good. There's no preferred vector length. There's no need to recompile. Now, when you get to an actual implementation of this stuff, there are considerations, of course. Fujitsu, for example, decided to implement SVE at 512 bits. So if you want to really get maximum performance, you should structure your code to be able to provide enough work for a 512-bit vector. Now, fortunately, HPC codes tend to be in that place already. So that is a good number for HPC codes. But in theory, we could take SVE all the way out to 2048 bits. And then that would be a very interesting platform to design for. You'd have to build a different memory system to feed that length of vector. One more example to really try to drive this point home. If you try to compare a vector length agnostic instruction set architecture like SVE with a traditional ISA with a fixed width, if we take a look at something like a scalar architecture, and let's say I need to do operations on 10 8-byte data types using a scalar architecture. Well, then I can use a loop and do 10 iterations over one 8-byte register. So it's like 10 little shot glasses, right? I do 10 little instructions of 8 bytes. Now, doing 10 instructions has a certain performance overhead, so you'd really rather do those with vector instructions. If you use a fixed width instruction set architecture like Neon, which has a 128-bit vector, and that's part of the instruction set definition, right? Neon instructions are always 64 bits or 128 bits, typically 128 bits. If I use a 128-bit vector engine, then I could do 4 iterations of a 16-byte register. So these are the large vector instructions. Plus, there's a little bit of a drain loop remainder of the bits of data that don't quite fill up the whole vector. And I'd use my scalar instructions for that. Now, you'll probably run faster here because instead of doing 10 instructions, I'm only doing 6. So even if the vector instructions have slightly higher latency or other associated costs, you probably come out ahead in the end. What vector length agnostic architectures allow you to do is use the same size register for every iteration of the loop, but then just dynamically adjust the amount of data that's operated on in the remaining remainder, the final iteration of your loop, so to speak. So in this case, I can do 2 SVE instructions with using the full SVE register, the full 32 byte, in this case, register. And then when I come to the final piece of data that doesn't quite fill the register, I just dynamically operate on only that part of the data which is relevant. And this is not the same as a bit mask. This is actually a different approach to where I've told the hardware that only so many bytes are actually involved in the computation. And there's a couple of key differences on how that works. Now, sizing the vector in that way is done through a concept of predication. So there are predicate registers which map operations onto vector lanes. So the number of vector lanes in a vector is unknown because we don't know how big the vectors are. We don't really know which vector lanes will be active until runtime, but the predicate lets us establish certain vector lanes as being active, and not only active, but involved in a particular type of computation. This has a lot of really powerful side effects. For instance, you can do things like vector partitioning and software managed speculation to allow you to perform vector operations right up to the edge of invalid pages in memory. That has a very interesting advantages when it comes to operations like string copy or strlen, which historically you wouldn't think of as vectorizing very well, but in fact with SVE vectorize quite well. And there are SVE implementations of strlen in hands-on if you want to take a closer look at that.
So John, there is a question on Slack. So the question is this. The dynamic nature of SVE seems like it would be challenging to avoid weird issues depending on which hardware the binary is running on. Running the same binary on a system that uses 128 as vector length may result in different results when the vector length is 1K. How much of a problem is that in practice?
That's a great question. The way to think about this is you have to think about it in a vector length agnostic approach. So you as a developer try to forget how many bits are in the register. Just completely forget that there's 128 bits in the local system. At the assembly level, the instructions, maybe I can show you this quickly. Like I said, there's a lot of reference slides in here, so some of this I won't be able to get to today. Okay, here's an example of assembly language that might help illustrate this. Take a look at this fmol instruction right here. Fmol z0.s p0/m z0.s #2. This is an SVE instruction that says in the z0 register, treat it as a single precision float. Use the predicate 0 with 0 fill, and then take the z0s register and multiply it by 2. Nowhere in this assembly language do you see anything pertaining to the width of the actual vector. So it could be 128, could be 2K, doesn't make a difference, makes absolutely no difference whatsoever. The assembly language itself, and it's not even clear how many bits are in a vector until you get down to the actual microarchitecture of this thing. Even the architecture doesn't know what it is. So in practice, it makes no difference. If you develop on a small vector and then run on a large vector, or develop on a large vector and run on a small vector, it's up to the microarchitecture to actually figure out how does that work in the real world. And in practice, it hasn't been an issue at all. We've had feedback from folks like Cray and Fujitsu who say that this is clearly the right way to build a vector instruction architecture, and it does in fact seem to work. I was highly skeptical the first time somebody presented it to me, but having worked with it for the better part of a year now, it is remarkably well engineered. I gotta say. A related point, right? If you don't know how big your vector is, but you need to iterate over an array of elements using vector instructions, how do I increment my array counter, right? I don't know how many vector elements I've operated on if I don't know how wide my vector is. There are special instructions that will return, that will update data based on the number of bits as reported by the microarchitecture. So for instance, if I say this increment W by 4, this is going to say increment the X4 register, this is an integer scalar register 4, increment the X4 register by the number of 32-bit lanes, that's denoted by the W in the instruction, the number of 32-bit lanes that actually fit in a vector length. So the result of this instruction is going to be different on different implementations of SVE, but the net effect is that I will still be updated by the right amount of, the right number of array elements that have been operated on. Similar consideration. If I don't know what the vector width is until runtime, how do I create compile time constants? There are instructions to generate sequences of numbers, to generate arrays of constants, to initialize values when they're first loaded, when the application is first loaded into memory. So for instance, this index instruction, I've said take the SVE register, which is operating in single precision floating point, beginning at the constant 1, increment by constant 4 until the vector is full. So in this instance, I can hold 8 single precision floats, and their values are 1, 5, 9, 13, 17, so on. They've been incremented by 4 until I run out of space in the vector. There's a very rich set of instructions around this sort of thing, and they're all public. You can go find them in the SVE reference manual that I've linked at the end of these slides. Right, I'm not going to get into the details around the registers at the moment. I'll just leave those here for your future reference. Now, in addition to being vector length agnostic, SVE brings in features designed to improve vectorization of existing codes. So codes with branches, codes with non-regular memory accesses. SVE has a very rich set of gather, load, and scatter store instructions, which in the Fujitsu architecture are implemented to amortize the cost of offsets in a page. So instead of having to issue a sequence of scalar instructions with offsets into a page, you can do a gather scatter or a gather load or a scatter store where those offsets are calculated by a vector instruction and data is broadcast to memory or pulled in from memory in that way. This is especially useful at the cache level where you want to avoid hitting invalid, excuse me, not invalid, but you want to avoid memory access patterns that cause cache line conflicts. Another view of the A64FX, including some performance numbers and benchmarks. I'm coming up on time here, so I'm going to wrap it up. Now, if I want to touch on programming tools very quickly, the right way to do programming with SVE is, if you can, link against a math library that already supports SVE. And I say this is the right way to do it because if you're already using BLAS, LAPACK, FFT, basic math functions, then all you have to do is relink your code and you're taking advantage of the SVE instructions. Hopefully, most of your code is spending time in those routines anyways, so you automatically are accelerating the hotspots of your application to begin with. Now, if you can't link against the library with SVE, a next option would be to use an auto-vectorizing compiler. GCC, LLVM, ARM compiler for Linux, Cray compiler, Fujitsu compiler, a variety of vendor compilers out there. The PGI compiler support SVE, and they do it through regular compiler directives. So if you're already using OpenMP parallel for SIMD or vector always pragmas, these will automatically generate SVE. There's some noise on the line. SVE has been well supported in open source for many years now. It's been in GCC since GCC 8. It's been in LLVM. It was first presented in 2016. So at this point, if you pick up a recent GCC or LLVM, you're not just getting bare bones support for SVE, you're actually getting a compiler with a pretty good job vectorizing. And the right way to do this is on an ARM platform, use mCPU equals native if you're on a system that supports SVE. If you're not, like unfortunately the Graviton2 cluster does not implement SVE. That's why we have to load the instruction emulator to do the SVE hands-on. But if you want to generate SVE instructions on that cluster, you can do it with this flag, march equals armv81 plus LSE plus SVE. The plus SVE tells the compiler to generate those SVE instructions. I've just about run out of time, so I want to point out that if you'd like to dig a little more into the intrinsics of SVE programming and even take a look at some assembly, have a look through the slides at the end of this deck. This will walk you through exactly what an SVE vectorization of a loop looks like and the assembly code that it generates. I'm very happy to answer any questions we might have about this. Find me on Slack or email. So again, encourage you to please do use the cluster. Do look through the hands-on materials as well as you can. If you run into any problems, just let me know. Don't forget to load the modules, see the hands-ons, follow the readmes. Do install the Forge remote client. And that's all I've got. Thank you very much.
Thank you, John, for the excellent tutorial here. Besides the questions which were asked on the Slack, are there any other questions from anybody?
There is another question in the Slack. This is actually a follow-up question.
Yeah, please proceed, read it. Yeah.
So a vector length has no impact on things like floating point precision, right?
That's correct, yes.
Okay, thank you.
Yeah, so each vector lane can be defined in its own floating point precision. I know, for example, single or double are supported. You can have half precision, B-float, although I believe B-float doesn't come until SVE2.
Okay, thank you.
Okay, so if there are no other questions,
thanks a lot, John.
Yeah, let's thank John again. So we'll switch to the next talk.